of kilometers away. Yet it has such a massive impact on us here on Earth. Life would be impossible without the sun. Almost everything can be traced back to the light and energy it provides, even though it's relatively close to us and not exactly hard to spot. There's still a lot we don't know about it, which is why both NASA and ESA have sent spacecrafts to study the sun in the last 2 years. These missions will be the closest we've ever been to our star, so close, in fact, that they will be able to directly interact with its atmosphere. So why are we sending these spacecrafts to the sun? What will they do there? What have they found so far? And what makes each of these missions special and unique? I'm Alex Molan, and you're watching Astrum. And in this video, we will investigate NASA's Park Solar Probe and ESA Solar Orbiter, and how they will explore our own magnificent star, the Music Sun. The Parker Solar Probe was announced in 2009 and was launched on August 12, 2018 on a Delta IV Heavy rocket. It will use 7 Venus flybys over nearly 7 years to gradually shrink its orbit around the Sun. At its closest point, it will only be about 6.16 million kilometers away, which is inside the Sun's corona or its atmosphere. Being that close would feel like 500 suns in the sky, beating down at the same time, with the temperature reaching up to 1,408 degrees C. The spacecraft is going 7 times closer to the Sun than any spacecraft has gone before. And at these temperatures, many components that are used to make sensitive equipment for spacecraft would melt away to protect the spacecraft and all its equipment. It is shielded by an 11 centimeter thick carbon composite shield which can withstand these high temperatures. This shield also has a wide reflective surface that can help minimize heat absorption. The shield will always be facing the Sun, protecting the spacecraft in this harsh environment, being far away from Earth and orbiting a very dangerous object. This spacecraft is by necessity as autonomous as a space mission has ever been. Because the heat shield always has to be facing the Sun for large sections of its orbit, it won't be able to point its antenna at Earth during these times of communication blackout. It will control each of the sensors, control the formatting of data products, and archive high-resolution data until it can communicate with Earth again and transmit back what it is. Captured as ESA's Solar Orbital Mission. Began development in 2012, and after 8 years, the Solar Orbiter was launched on February 10, 2020, on an Atlas V rocket. The Solar Orbiter will also use gravity assist from Venus, as well as Earth. These swingbys will put the Solar Orbiter into an initial 180-day orbit around the Sun. The spacecraft will reach the closest approach the Sun every 6 months at around 43 million kilometers away. This is comparatively much further away than the Parker probe's closest approaches. But just to give you an idea of the temperatures at this distance, still at 43 million kilometers from the Sun, the temperature can reach up to 500 degrees C, as the sunlight will be 13 times more intense than what we feel on Earth. The Solar Orbiter is protected by a heat shield made with titanium foil layers about 40 centimeters thick, which is not as effective as the Parker probe's heat shield, but still enough to protect the spacecraft on its dangerous mission. It is surprisingly difficult to get a probe into a close orbit around the Sun, as it takes 55 times more energy to go to the Sun than it does to go to Mars. You see, the Earth is always moving sideways relative to the Sun at very high speeds, about 30 km/s or 108,000 km. In order for a probe to successfully enter into an orbit around the Sun, it must cancel out almost all of that motion. This is why both the Parker and Solar probes were launched using 2 of the most powerful launch vehicles available at the time, the Delta IV and the Atlas V. The objectives of the Parker Solar Probe and the Solar Orbiter are similar to a great extent. Both these missions aim to find out more about our Sun's corona, its solar winds, coronal mass ejections, the structure of the sun's magnetic field, and simply how it all fits together. The sun, like all stars, is a ball of plasma. Plasma is superheated matter, so hot that the electrons are stripped away from the atoms, leaving an ionized gas. The sun has an atmosphere of extremely hot but tenuous plasma, extending out from millions of kilometers, called the sun's corona. You can see the plasma atmosphere in this image, although typically it is far harder to see than the sun itself, as the sun's outer layer, known as the photosphere, is much brighter. The ideal time to spot the sun's corona is during a solar eclipse, when the moon blocks out the photosphere disk, leaving just the wispy arms of the corona. Visible, the strange thing about the sun's corona is that its temperature is between 1 million and 3 million degrees C, whereas the sun's surface temperature is only about 5,500 degrees C. And currently, we don't really know why, and while the sun's corona looks substantial, its brightness is deceiving. It is actually magnitudes less dense than Earth's atmosphere. The sun continuously releases huge amounts of plasma and radiation into space, which is known as the solar wind. Solar wind is not very strong or dense, and the Earth's magnetic field diverts most of it harmlessly away, while a lot of solar wind does get redirected around the planet. Some gets funneled towards the planet's poles, where ions from the solar wind collide with atmospheric oxygen and nitrogen atoms, the interactions of which emit the beautiful colors we see in auroras, the number of particles.